I'm going to start with the remove again, because this is probably the most complex function we're going to see all semester, or method. And there's like three parts to it. There's the public remove that kind of deals with the special case of like, okay, the root. Or it calls the recursive remove. So let's have another quick look at the public remove. Well, first and foremost, it checks, does the thing exist? If it doesn't exist, it's not going to try to remove it. It's going to return false. Otherwise, we start a binary search for the element in the tree by calling the recursive one. And then once everything's all done, it's going to reduce the size and return true as if it was successful. So here's the recursive remove. And the recursive remove starts by saying, okay, first of all, remember like we said last time, it's not possible for current to be null in this particular situation because we confirmed that it exists. And the only way it could get to null is if we had a tree. Let me grab a marker here. Like imagine I had a tree like 10, 15, 5, whatever. And I was looking for, like, I wanted to remove the number 16. Okay? But it's not there. And I can conclude it's not there because when I'm at the 15, if 16 existed, it must be here. And if it's null, if there's nothing to the right of 15, if there's nothing where it should be, it must not exist. Because it's not possible for 16 to be anywhere else. So that's why if we confirm that it exists, it's not possible for this to ever be null. Because if it exists, it can't be null. There must be something seriously wrong. There must be a serious bug somewhere if that ever happens. All right. So otherwise, we start doing a binary search for the thing we want to remove. If we didn't find it, we just go left or right accordingly. But when we do find it, so when comparison is 0, when we do find it, we need to, first of all, figure out, okay, we have access to, through the parameters, we have access to the current node, the one we're looking at, and its parent. But interestingly enough, we don't know if current is actually the left or right child of the parent. We don't actually know. We have a parent, we have current, but we don't know if it was the left or right. So that's what this is doing right here. Is, okay, we're removing a node, and we want to find a replacement node potentially. It could be null, the replacement node. But the parent, like if I'm removing 15, the parent's right child needs to get updated. If I'm removing 5, the parent's left child needs to be updated. But all I know is that I have a parent and a current reference variable. I don't actually know which one's which. So that's all that it's doing there. It's like, okay, well, which is it the parent's left or right that's being removed? That's what that check is doing. But all this is a binary search through our tree until we find what we're looking for. And then when we find what we're looking for, when we find the thing we want to remove, we call this other method find replacement node. And it looks hairy, but when we break it down into its parts, it's not too bad. In fact, we've already talked about all the different cases. So let's say, so we have reference to a node from the parameter list. There's only one, the node to remove. So if the node we want to remove has a left and right of null, we can conclude that it is a leaf node. And then we just return null. Because that means if imagine I'm removing 15, it's a leaf node. So what do I want to update the parent's right child to be? Nothing. Set it to null. Yeah? So far so good? Now, if the node's left is not null, but the right is null, meaning we have something like this. What do we do in this situation? And this node may or may not have children. It doesn't matter. But if this is the situation, all we do is we pick this to be the replacement node. Just promote it. Yeah? So far, so good? And similarly, if it was like this, just promote the 17. It's only when we have a case where we have something like this where it gets a little hairier. This is where we have work to do. So, I'm going to try to draw out an example. Ten, 5, 20, 11, no. 17, 18, 15, that's a 14, okay? So let's say I want to remove the 20. No. What do I want to remove here? What's a good example to get rid of here? Okay, let's say I remove the 17. All right? This is what I got. I want to remove the 17. No. Let's remove the 10. Let's remove 10, okay? For all we know, this has a parent. Who knows, right? I'm removing the 10. The trick, remember, it's one of two things. The one we're going to do is so we want to remove 10. So we want to find the next smallest number in this tree that's bigger than 10. That's what we're going to do. Where that will be, it will be this subtree's smallest element. And remember, when I say this subtree, I mean everything under there. The smallest element in this subtree will be the next biggest thing after 10 that exists in the tree. Alternatively, we could do the opposite, where you find the next smallest thing after 10. But the reason I'm going to go to the right is because with our rules of duplicates, we always put duplicates to the right. So it would be possible to remove 10 and then put another 10 back in there, so the tree is like pretty consistent, which is, there's no real value there. I just liked it. All right? So this is our situation. We want to remove, what do I have this? This is called to remove. Call it TR. So this is our situation. So far, so good? All right. So that's what's going on once we get to here. So I start by saying, okay, so parent equals the element I want to remove. I'm going to, can you see that P at the back, or is it covered? You're good? Do you see it? Okay, cool. So that's parent, and then our current is going to be 2 removes right. So we start like this. So this is where we're starting. So that's lines. I guess I don't have line numbers here. but that's right after the else. So far, so good? Any questions, thoughts, concerns, comments? So then I say, okay, what's the comment? Find the in-order successor. 2 removes right child's leftmost node. Find the minimum, find the smallest element over here. And remember how we found the smallest element. Just keep going to the left until you can't go to the left anymore. So we look at this tree, we know it's 13. But we got to find it programmatically. So what do? We say, okay, while the current's left isn't null, so this is current. Is its left not null? No, it's not null. Move parent down to here, and then current moves to here. All right? Is current's left not null? No. Keep going, current, parent. I'm working through this because I think it makes it a lot easier to follow. But if after this you don't understand it, just work through it again with examples and it'll click. Is current's left not null? No, move it down. Is current's left not null? False. We stop. So now we're at the situation where we have our replacement node here, 13. I want to put 13 where 2 remove goes. But there's a problem because it has a right child. We can't leave this dangling. I mean, it might not have a right child, that's fine, and if it does, it's null. But it's possible that it has a right child, and we got to figure something out there. So what do? So there's a giant, okay, so replacement node gets set to current. Okay, I basically just relabeled it replacement node because I think it's a better name for it. Makes it a little easier for me. So we got replacement node as current. Then I say replacement node, set your left to removes left. Meaning this node's left gets set to removes left. Okay? I'm not going to draw that. I guess it's just the 5. I mean, this could be who the hell knows what, right? I'm not going to draw that, but we set the 13. So it's like I'm putting the 13 here, but I haven't really done anything with its right child yet. So this is kind of like we're halfway there. Okay, then I've got a giant comment there. What does it actually say? Update replacement nodes right if necessary. If the in-order successor of 2 remove is its immediate right, no update is needed. Otherwise, the replacement node's parent's left is set to the replacement node's right, and the replacement node's right is set to the 2 removes right. What? Let's just see. Sometimes English explanations make less sense than the actual code to me, so let's see what the code says. What does the code say? All right, so 2 remove, is its right equal to the replacement node? No. It's possible, imagine for a second, there was nothing here. Okay? There could be more over here. It doesn't actually matter. 20, 25, 21. I'm just going to add a couple more nodes for the fun of it. 30. Okay? But imagine none of this is here. Right? That's kind of like the case it's talking about. It's possible that the replacement node is the root of the subtree. Like it's possible that the root of this whole subtree is the smallest element, right? That's the case it's talking about. All right, so if it's not the replacement node, what do? Okay, parent. So parent right here, its left is set to the replacement node's right, the 14. That's safe because we know that the 14, although it's to the right of the 13, it must be less than the 15 because it was to the left of it. So it's safe to move this up. And remember, this 14 might have a billion subtrees. Actually, it could have 2 subtrees, but they could be huge. So we move the 14 here with its subtrees, whatever, they're left the way they were, if they exist or not. And then replacement node, your right is 2 removes right. So replacement node, that's what, well, that's not this anymore, actually. This should be. Okay, your right is now the 2 removes right. So there. It's now set. Yeah, we like this? No? Yes? No? Then in the end, we return the replacement node, a reference to the node that's now been replaced. Do we like it? I like it. Realistically, this is, if it's not the most complex, and when I say complex, I don't mean complicated. There's a difference. Has anyone ever hear this before, the difference between complex and complicated? Complicated is something that's really hard to wrap your head around, right? And it's just kind of chaos and crazy. But a watch is complex. It's sophisticated, but you can break it down and understand the parts. This is complex. It's not complicated. That's the nuanced difference there. But this is going to be the most complex, and if not the most complex, it's going to be the top 5 most complex things that we're going to look at this whole semester. So if I explain this to you and you understand it completely at this stage, I don't know if I believe you. This is going to take some time to really wrap your head around. It's all there. All you have to do is follow through, do a couple of examples, and you'll understand it. But you gotta make sure you put the time to figure this out. You bet your ass something like this is going to be on the test. So make sure you take the time to really get it. I went over it last time quickly. This time, much more better, I think. But yeah. So are there any questions, thoughts? Yeah.
So on the final, are we gonna have to write the remove?
I don't know. I can't, what do you do? I can't answer these questions. I haven't made the exam yet, so I don't know. When is the exam?
20th.
20th? A Saturday?
Yeah. Morning. Yeah. Saturday morning, 9 a.m.
Huh. That's going to be a problem. All right. I could always cancel it, yeah? Do you think so? Okay, so yeah, any other questions, thoughts, concerns, comments, observations, points, anything? I like this. I like this because I think it's written in a way that makes it as clear as it can. Yes, yeah.
If your objective was to balance the tree, could you just throw everything there into a sorted bag and then divide size by 2 and start setting up the tree via the middle of the bag, and it would just take the middle one?
Yeah, but there are better ways to do that. But, I mean, that is a strategy, but you'd have to rebuild the tree every time, which is going to be linear time, where this remove is going to be log n time. But there are tricks and things people do for balancing trees. The AVL trees will be one that I think you'll learn next semester, or next year, but yeah. But yeah, so I like this here because I like how complex it is. It's non-trivial to understand. But if you're here at this point of the semester, you absolutely have all the skills you need to understand this. And I really like it, this one, and I guess it's kind of hard to explain why. I like how complex it is. But there's a cleanness to it. I don't know how to explain it, but
Quick to explain what is happening, but the steps to get there takes a little bit.
to me, with the way it's written, it aligns with the ideas that we need to follow well. It's intuitive. But it's not intuitive when you look at it quickly. When you look at it quickly, you go oh my God. But once you take your time and look at like, okay, the couple of parts, you start to see like, oh, okay, this part is that case, that case, that case. Now we got to find the minimum. How do we do that? Just keep going to the left until we run out and then update the children accordingly, right? I'm not trivializing any of those parts, but when you break the problem down into the parts, I mean, we can play that game where we get less and less abstract as we go. This is clearly a fairly high level abstract discussion of it. But I don't know, I like the way the parts break down in this particular example. Last chance for questions on this? All right. Okay, there's the remove. Yeah, okay, this is just explaining it. Contains, it's a binary search. We've gone over this a million times. Count, it's a binary search, except this time we increment. We return 1 plus the count. That's all, if we ever find it. Yeah. Any questions about linked binary search trees? All right. Sorting. We talked a little bit about sorting last semester, right? Very little though. Like we barely touched on it, if I remember correctly. I think I blitzed through a couple of examples in section 11, but I don't remember if we got to it in section 12. Who here was in section 11 last semester, in Mulrooney? Okay, so do you remember like we did some sorting in front, we sorted people by height? Who was in section 12 though, in the Schwartz building? We didn't though, did we? I don't think we had time. Okay, but yeah, okay, we didn't, I don't think we had as much time in that section for whatever. I think the way canceled classes worked out with, yeah. All right. Sorting. So, like searching, sorting is a common, popular problem to talk about in like first year computer science. And there's a couple of reasons because, I mean, everyone's sorted something before. You understand the problem well. It's not this complex problem to understand. The problem itself is fairly straightforward. I have this collection of things. I want to sort them. So you understand it really well. So like, raise your hand. Have you ever sorted anything in your lives? Of course you have. Everyone has. But how much did you think about that? Like, how much were you like, what were the steps I did to sort? You probably didn't think about it, and let alone, you probably didn't think about the amount of work that was involved. And the reality is, so raise your hand if you've sorted anything before in your life. Yeah, you all suck at it though. You've all done a really bad job. Yeah, you've all done a terrible job at sorting things. Because chances are, you've followed along, or you've probably done one of the 3 common sorting algorithms that we talk about. Insertion sort, selection sort, and bubble sort. You've probably done this before. The idea behind bubble sort is you've got an unsorted collection. You start at the beginning and you compare adjacent elements. They're right next to each other, index 0 and index 1. If they're out of order, you flip them. If they're not, you leave them alone. You go to the next pair. You look at index 1 and 2. If they're out of order, you flip them. If they're not, you leave them alone. And you do that all the way till you get to the end. But after one pass, it's not sorted. You won't have the elements in order after one pass. But what will happen after one pass, and we're going to go into more detail of this particular algorithm as we go through this topic. I'm just giving you like a primer right now. After one pass, what happens is the biggest element bubbles up to the top, to the back of the collection. The biggest element will be where it belongs after one pass. You just keep doing this process until it's sorted. Selection sort I'm afraid I'm going to mix up selection and insertion because they're similar. What you do is you go through and you find this. I've got an unsorted collection. Okay, just think of like a bag, an array, whatever. What I'll do is I'll create another collection over here that's empty. And what I'll do is I'll go through and I will select the smallest thing and then add it over here. I'll do it again. Find the remaining smallest thing. Take it out, put it over here. And keep doing that until I'm out of things over here and, well,
I think selection sort's in place.
it doesn't matter. You can do it in place or not. It doesn't matter. It's usually easier to talk about it where it's not. What he meant was you can sort it in the same like container, but it's usually easier to just talk about it if that doesn't actually matter. And then there's insertion sort. What you do is you go through, why am I forgetting these right now? This is bad, I should know this. Selection sort, you go through and you select the next thing. Insertion sort is, you've got a sorted collection. Sorted collection, unsorted. Backwards. Unsorted collection, I want to sort it and put it over here. So what I'm going to do is I'm going to find the element that belongs. Well, I keep mixing up selection sort and insertion sort. This is bad. Now I'm testing myself if I could actually remember it before I give up and look at it. Insertion. So imagine I've got some collection that's like, yeah, okay, here we go. Here's what we do. I got it this time, I promise, I swear. Unsorted collection, sorted. What I'm going to do is I'm going to take something from here and put it where it belongs over here. When it's empty, it just goes into the beginning. I then arbitrarily select another thing. I go and put it where it belongs over here. Does it go before the element that's in there or after? If it goes before, put it before. If it goes after, put it after. Do it again. But what I do is I go through the sorted collection and I insert this element where it belongs in the sorted collection. That's the idea. All right, so sorting problems, okay, order, yeah, things need to have an ordering, yeah, okay, BOGO sort. Here's the first sort I'll talk about. Given a function called isSorted, all right? That will return true if the collection is sorted, false otherwise. What's the computational complexity of that? It's linear. I have to look at the collection, all of them, to figure out if anything's out of order. Sound good? Okay, so that's linear. And then I've got a function called shuffle that just randomly shuffles the collection. Think of like a deck of cards. I'm shuffling a deck of cards. That's going to take linear time too. All right? So here's the idea. Take my unsorted collection, shuffle it, check if it's sorted. If it's sorted, I'm done. If it's not, do it again. Check if it's sorted. If it is, done. If not, do it again. This is a terrible idea.
I have it here in Google. It's also called stupid sort.
There you go. Also called stupid sort. Yeah, it's pretty rough. So while not is sorted, shuffle. So like, in principle, this could go on forever, right? It's possible that the collection never gets sorted, right? Like that's possible. This is a terrible collection. But what do I have here? So if n is very small, there's a reasonable chance to end up with a sorted collection after a while. This is true. If I were to even just go in Java, whip this up with like, I don't know, and do BOGO sort, it'll sort it pretty quickly, right? N's a pretty small number, but there's 8 times 10 to the 67 permutations of a deck of 52 cards. Okay? That's a lot. 52 cards. What's that thing like? If you shuffle your deck of cards, there's a good chance that that ordering has never existed before? Well, To put it in perspective, there's roughly 2.4 times 10 to the 67 atoms in the Milky Way. You're going to run out of atoms in our galaxy. It's crazy. It's nuts. Anyways, so what were you going to say?
And if you're randomly finding a permutation, then it's not even like.
It's worse.
It's not even guaranteed that you're actually not going to repeat the same one.
Exactly. It's possible, insanely unlikely, but it's possible that I shuffle the deck and I get the exact same permutation I did a moment ago. It's possible. It's very unlikely. It's about that likely, but it could happen. So here's bubble sort. Here, let me click this and then maybe it'll restart. Oh, if you click it, it just goes to the wiki article. All right, well, don't look yet. Don't spoil. All right, there we go. Are they out of order? If they are, you switch them. Are they out of order? If they are, switch them. Out of order? Switch them. Out of order? No. Out of order? Yeah. Out of order? Yeah. Out of order? Yeah. 8 must be where it belongs. We just repeat this process.
I think it looks cool with bars. And then you can see how the tallest goes up, and then kind of.
I don't know. I could see that 8's bigger than 7. So why is it that the biggest is guaranteed to make it to the end? Well, I mean, even if 8's at the beginning, if they're out of order, I switch them. And then I move to the next pair, and 8 will be in that pair. If they're out of order, you switch them. It's guaranteed that after one pass, the biggest thing will be where it belongs. So what do you think the computational complexity is to do one pass? N. You look at all n things. So one pass is order n. If I have n things that I want to sort, and after one pass, one of those n things is where it belongs, how many passes do I have to do to guarantee that I end up with a sorted collection? This is not a trick question, and if you're having a hard time with it, listen to the question again carefully. I have n things I want to sort, and after one pass, one thing is where it belongs, right? But I want to sort n things. If one pass gets one of those n things where they belong, how many passes do I need to do if I want to get all n things where they belong? N minus 1. I know, I'm being a dick. Like n, right? Now it's n minus 1 because watch what happens for this last one, right? When the second last thing gets where it belongs, the last thing will always end up where it belongs too, because it can't go anywhere else. So that's why it's the n minus 1. But yeah, we're lazy computer scientists. We're it's like n. So you have to do n passes. And how long does each pass take? N. So if we have to do n units of work, n times, how much work am I doing? N squared. No, not factorial. No, we're good. No, nowhere near factorial. Thank God. So it's going to be n squared. We have to do n things, n times n. Now, you will notice that, the first pass, I have to look at everything. But the second pass, I don't. Because I know the last element is where it belongs. So there's no need for me to actually look at the last element after one pass anymore. And then after 2 passes, I don't need to look at the last 2, and so on. So actually, every single time I do a pass, I have less work to do for the subsequent pass over the collection. But, let me erase this. You may recognize a similar pattern. So really, I'm comparing adjacent elements. So if there's n things, how many adjacent pairs are there? There's n minus 1. But we're going to be lazy and just say n for the sake of simplicity here. So on the first pass, I have to do something that takes n time. But on the next pass, I actually only have to do n minus 1 things. N minus 1. Because there's one less thing to worry about. And then n minus 2. To like 2 to 1. Right? Does this look familiar to you? Please say yes. Yeah, okay, good, right? Oh, it's the arithmetic series. That's like the n times n minus 1? Divided by 2, something like that, right? Yeah. And then, oh, that's like n squared. It's n squared, right? It's n squared. It's quadratic. Any questions about that? So that's the idea. Here I'm just walking you through the examples. So worst case scenario. What's interesting about this sort, though, is you can stop early. If I ever did a pass on elements, if I ever do a pass, so let's say I give you the numbers like 1, 2, 4, 7, 6, right? It's not sorted. It's almost sorted. But I'm going to do one pass. Okay, they're fine, they're fine, they're fine, they're not fine. So I'm going to switch these, 6, 7. Okay, I did a pass and I made a swap. Now I'm going to have to do it again, all right? They're fine, they're fine, they're fine, they're fine. If I ever do a pass and nothing got swapped, what can I conclude? It's sorted. So I can actually stop this early. I can stop early by being like, well, if I ever complete a pass and never swapped anything, I'm done. Which is great, because it's possible to get a collection already sorted. And if that's the case, the computational complexity of this search, this sort, is linear. I do one pass, and I don't change anything. And there we go. We're good to go. But we have a worst case scenario situation, and that's if we get the elements in reverse order. Then we have to do all n minus 1 passes. So what's interesting about this sorting algorithm is there is a best case scenario where the configuration of the data matters, and a worst case scenario based on the configuration of the data. Pretty neat, eh? I think so. But, you know, when we talk about computational complexity with big O, we're always focused on the worst case scenario. This is just explaining the best and worst case scenario. And here's like the algorithm for it. Well, the list is not sorted for each adjacent pair of values. If they're out of order, swap them. Note that the list is not yet known to be sorted if I ever had to do a swap. That's it. That's it. That's the algorithm. Pretty simple algorithm. And what I really want to emphasize here is the bubble sort algorithm is this idea. No one implementation of bubble sort is bubble sort. It's an implementation of bubble sort. Bubble sort is you scan and you swap adjacent elements if they're out of order. That's the spirit of bubble sort. That's the idea. No specific implementation is bubble sort. They're implementations. That's it. Any questions about bubble sort? So now insertion sort. So here's an example of insertion sort where it's being done in place. Basically, we're only using one collection, one container of data to sort it. But here's the idea. 6, where does it go? Okay, 5, where does it go relative to the sorted part? 3, where does it go relative to the sorted part? Where's 1 go relative to the sorted part? We find where it goes and we insert it. 2, where does it go? There. 4, where does it go? There. That's insertion sort. Cool? That's the idea. Just like with bubble sort, where the idea of the algorithm is compare the adjacent elements, swap them if they're out of order, keep doing it until it's done. Insertion sort is keep taking elements and insert it into the sorted part where it belongs. That's insertion sort. That's what matters for insertion sort. By the way, these are all stolen from Wikipedia. If you click the images, it takes you to their respective things. I think I just sped up the GIFs, though, because they were a little painfully slow. Yeah, okay. Computational complexity. So I'm just going to read this one to make sure I don't miss anything. Okay, to think of the complexity, consider a list of size n. For each element selected, the location in the sorted list where it must be inserted needs to be found. So I know we just saw the animation where it showed the start and it did it the whole time. But imagine I'm at some arbitrary point in this sort, okay? I've got a total of n things that need to be sorted, and some number of them still need to be sorted, and some number of them are already sorted, okay? I take some arbitrary element here. I need to go through the sorted part and find where it belongs. What's the worst case scenario in terms of computational complexity of how long it'll take me to find where it belongs? I got to look at all elements. Maybe it has to go to the end. I don't know. Right? I mean, the first time, when the sorted part is empty, I select one element. How many things do I need to compare it to in the sorted part? None. It goes there. The next time, I have to compare it to one thing. Then the next time I have to compare it to two things. 3, 4, 5, n minus 1, n minus, So we still have that arithmetic series thing going on. Think about, let me slow it down to make sure. I may have done this a little too fast because I am aware of the time. I have n things to sort. I take the first element. I have to compare it to 0 things over here. I take the second element. I compare it to 1 thing. Third, to 2 things. Fourth, to 3 things. When I take the nth thing, how many am I comparing to? N minus 1, right? How many things did I have to insert? N. The first time it took 0 units of work, then 1, then 2, then 3, then 4, then 5, then 6, then 7, n minus 1, all the way up to n minus 1, right? It's the arithmetic series again, right? The first time it was 0, plus 1, plus 2, plus 3, plus n minus 2, plus n minus 1. How many things are here? There's n terms, right? So we have this arithmetic series, it's quadratic. But like bubble sort, there is a best and worst case scenario configuration. Because it's possible for me to take the element and say, okay, now this will really depend on the specific implementation rules we set up for our insertion sort. Let me go back. Look at this example. I'm going to give you a minute. Look at this example and try to think, what is the configuration of the best case scenario and worst case scenario with this example here? Does anyone have any ideas?
It's already sorted, then linear.
With this implementation, the way it's being shown here, the way this algorithm is being done, if this data is already sorted, it's going to be linear. Because each time we'll only end up ever comparing to the first thing. Like watch in this example, right? Right where it just showed, okay, we want us to insert 8. Oh, it goes right here. We left it alone, basically. But when the number is really small, it's got more work to do, right? So 5 goes before, 3 goes before. But pay attention to 8, right? So where does 8 go? Well, 8 goes after the 6. Oh, we only had to do one comparison. We only had to take the 8, compare it to the 6, and go, oh, it goes after 6. So with this implementation, if the data was already sorted, we would only actually ever have to do, take the one thing, compare it to nothing. Take the next thing, compare it to only the first thing, and it goes in front. It goes in front of that thing. Here, I guess, behind because of the direction. But this assumes the configuration of the data already being sorted assumes, that being the best case scenario, assumes that we are scanning from biggest to smallest. That we're scanning in this direction. There's nothing saying I didn't take the 2 and start, okay, does 2 go before, after 1? The side that I start scanning from is entirely arbitrary. It doesn't matter. So if I started scanning from the other direction, what do you think the best case scenario would be for the configuration of the data? If it's in reverse order. Because I would take 8. Imagine I took 8. Where does it go? Oh, it goes in the front. I take 7. Where does it go? Oh, in front of 8. Take 6. Where does it go? Oh, in front of 7. Really, the best case scenario is the configuration of the data such that it only ever actually has to do one comparison every time it does an insert. The worst case scenario is the opposite. And again, that depends on the directionality. If we do it like this, the worst case scenario would be if the data was in reverse order. Because then every single time it would do the maximum number of comparisons for the insert. Here's the algorithm. For each element in the unsorted list, scan the sorted list to find where the new element goes. Insert the new element into the sorted list. That's the algorithm. That's it. Anything more specific than that is unnecessary. That's insertion sort. And then finally we have selection sort. This is an example of the selection sort taking place in the same container. It doesn't need to be. Here, scan for the smallest thing, put it where it belongs. Scan for the smallest thing, put it where it belongs. Find the smallest thing, put it where it belongs. Find the smallest thing, put it where it belongs. That's insertion or selection sort. We go through and we select the thing we want and put it where it goes. You may, if you spend some time thinking about it, you'll see that selection sort and insertion sort are actually kind of the exact same idea, just kind of flipped a little bit. Insertion is you find the thing and you look where it belongs. Selection is you know where the thing, you know what
Spot you're trying to put something.
exactly, right? So it's just kind of like flipped. Sadly, I don't think we'll have time to have fun with this one, so we'll stop here for today. Did we have any questions? So going on my note from earlier, there is a lab today if you have Friday lab.